Okay. Thank you very much, Bastian, for the introduction. Once again, my name is Jiří Valena, and I'm a business manager of company UptimAI. We are a Prague-based startup, and we work on the so-called uncertainty quantification solution that's helping the engineers working with the simulation to bring the simulations closer to reality. Another goal of our tool is to simplify the decisions and provide deeper simulation insights for engineers. And I think I will start with a team introduction. So our CEO and CTO and founder, Martin Kubíček, is the brain of our company. He's the one who actually came up with the algorithm. We have head of applications who is Tomáš Koutník. He's really experienced engineer. He leads the team that's working on the implementation of a tool and so on. And myself, I take care of everything that is non-technical, I would say, in our company. I will now start a video that was done with in the cooperation with ESA Business Incubator Center about our solution. It is 2 minutes, and I think it can explain nicely what we do, and then we will go deeper into the presentation itself.
The rocket goes up, and at a certain height, it loses its boosters. Where do they land? There are plenty of uncertainties in these calculations, and it can be greatly affected by small disturbances such as temperature fluctuations, wind directions, or pressure changes. Remember the infamous butterfly effect? A small change in one state of an input condition can result in large differences in a latter state. We call this kind of calculation the propagation of uncertainties. It sounds like fuel for a spaceship heading to infinity and beyond, but it is a real deal in the space industry. Space engineer Martin Kubíček came up with an algorithm that can crunch all the data and uncertainties, analyze them, and give them the structure and clarity in the form of the probability model. The probability model can be further understood and reduced, which enables it to have better accuracy, overcome critical moments, and reduce the costs. Engineering processes, like a plane or car design development, face the same issues with uncertainty similar to booster landing. For example, how will the change of rear rail's diameter affect the car if the driver steps on the brake while driving 60 kilometers per hour? How about at 150 kilometers per hour? For calculations like this, Kubíček's company UptimAI developed a unique tool, an algorithm, and engineering probability data cruncher per se. Same as with the rocket ship, UptimAI can crunch the numbers and give you a better answer than any supercomputer can. Quantification, solution, and reduction. UptimAI answers the question of probabilistic engineering design. With mathematical modeling, it reduces risks and saves money. Meet UptimAI, one of the incubatees in the European Space Agency Business Incubator that brings space for your ideas.
Okay. So as the video said, our tool was firstly developed during space research activities by our founder, Martin Kubíček. And Martin originally developed this solution to estimate the impact area of space debris. Then ESA realized that the solution is really interesting and it can be used in a wider portfolio of applications. So they invited us to ESA Business Incubator Center in Prague, and we become a part of so-called technology transfer, and we redesigned this tool to be used in computer-aided engineering. And what makes the tool special is the fact that it combines Martin's fundamental mathematical discoveries with elements of artificial intelligence and machine learning. We shortlisted 3 main difficulties that engineers in simulations were facing. And we realized that the most common one is that sometimes it's hard to understand dependencies between inputs and results of simulations, especially when there is a lot of inputs. Secondly, when you have multiple changes of inputs at the same time, it's hard to understand how these changes are interacting with each other. And then you always need your product to work well in the whole range of operational conditions. And this is quite complicated. So this is the third thing that we are solving using our solution. What our solution does in a nutshell, we connect our tool to simulation platform, and it automatically generates a mathematical model which describes dependencies between inputs and results. Then when the model is ready, it provides engineers with a deep insights, what's happening inside the simulation and what they need to change in order to design a good product. And thanks to the artificial intelligence, we made our tool highly adaptive. So we can build a model really fast. So we can cut the total number of simulations by up to 90%. Here you can see what I already described a bit, but in more detail. So this is the process, and you can see how it works. First, we always connect our tool as the add-on to simulation platform, and we can connect it to any platform in the market because our tool is purely mathematical. Then, when it's connected, the engineer enters the ranges of inputs and select the results that he wants or she wants to achieve, and starts running the simulation. And our tool starts running the simulation repeatedly, always with a different set of inputs, and it's building a mathematical model or so-called surrogate model on the background. And when the model is precise enough, because you set the precision first, it provides insights to an engineer in very clearly readable, and it provides a really easily readable outputs to the engineer. Here you can see some unique features that we have. So we have incremental function where you can see the dependencies between 3 and more inputs at the same time. Then we have a sensitivity analysis. What makes our sensitivity analysis special is the fact that you can see how influential is each input and how influential are the interactions of this input. And then we have a preliminary optimization, and it shows you a range that you want to achieve for each input parameter to have a product that works well. We have much more features than that. You can check them out on our website. These are just free to give you an idea of what we can provide. So I'd like to summarize the benefits. Using our tool, engineers can significantly reduce their workload because we can simplify the decision-making process. We provide them insights, and when they use them, they are able to approach the task strategically and see all those dependencies and connections between the inputs and results, and hence they can improve their product in a very easy way. And it can uncover unexpected product behavior and its reason because we can show engineers what is causing the troubles, what a combination of parameters, and how do they need to change it in order to make the product a better product. Now I will go to case studies. I have 3 case studies here, so I'll spend some time on each of them. The first one is called car box beam deformation. It was done with Skoda Auto here in Czech Republic in cooperation with Mekas SE. And we had the part, which is this part that you can see here. It's a welded beam, welded from 2 parts, U part and I part. And we have a bumper here that's hitting the beam, deforming it. And the knowledge gained from this test is then used to improve the passive car safety. The goal in this task was to understand the influence of input characteristics. Then we needed to understand what's influencing the total energy that is absorbed during the impact. And we wanted to design these parts to be insensitive to conditions of physical testing, because there was a big range of the results before we implemented our solution. We had 27 inputs here, geometry, some material properties, and some others. And we were solving it in FEM environment PEM crash. Here you can see some technical findings. So we realized that friction between this bumper and this welded beam needs to be increased, because it's causing this tail in absorbed energy. So we can actually do the part much more insensitive to the testing conditions if we increase the friction. Then we realized that they need to build each part with a different thickness, because when there's the same thickness of each part, it's not absorbing that much energy. They initially thought that they need to increase the thickness of each part, but it was making the test more expensive, because there was they needed to use more material, obviously. And we realized that it's not that important to make it thicker. They just need to have different thicknesses, because then it causes so-called guided collapse, and it can increase the absorbed energy. Another finding was that spot welds positions must be non-equidistant. So you can see the spot welds here. And again, they thought that they would have to add more spot welds, but we realized that it's not that important to add more, but they just must be non-equidistant. And using our incremental function, we realized that if you combine a barrier rotation, Young modulus, and absorbed energy, when the Young modulus is below the 200 gigapascals, there is a significant drop in absorbed energy. So they need to use the material that has a Young modulus higher than 200 gigapascal to achieve a good absorbed energy, great amount of absorbed energy. Here you can see the results. So we help them to better understand the impact behavior. And thanks to it, they were able to increase the absorbed energy by 10%. So you can see here from 2000 to, we went to the area of higher increased energy. And we were able to decrease the range of results, because it was ranging from 2000 to 2400. And here you can see that the range after implementing our tool was much smaller. And all of this we were able to do only with 280 calculations instead of 4060, which would be required with some polynomial chaos method. The thing is that our tool was, the one calculation took 1 hour in this case. So it was a huge save of computational power and the time as well. Another case was done with a company, Altran. It's a local branch of Altran here in Czech Republic. And the goal was to investigate stress and forces on this tripod. This tripod has 3 actuators that are displacing in order to move the top plate, which holds optical element on the top of it. We wanted to find out what are the possible ranges of manipulator movements and estimate the forces and stress levels, and to find out what is really causing the increase in stress and so on. We had 12 inputs. These were actuator and spring configurations, then displacements and spring pretensions. And it was done in FEM environment MSc Nastran. Here they were wondering if there is any connection of the actuators, if there is some actuator that is affecting the stress more than the other ones. And we started with looking at individual actuators, and we realized that, as you can see here, actuator displacement alone cannot eliminate the stress completely. So it can decrease the total amount of stress, but it cannot eliminate it completely because there is a spring pretension. So stress cannot be decreased under 100 megapascal. Then we realized that any actuator displacement increases stress. So it's not that some of them are more important than the other ones. It just increases stress when they are displacing. And then we looked at the sensitivity analysis, and we saw that the interactions of the parameters cannot be neglected. And here you can see that, that there is a notable influence of all the displacements. So when it comes to the stress in this part, it's all about displacements. So it would be good to focus on the other parameters, such as spring positions and spring pretensions, because these are not affecting the stress that much. And the last thing was that we found out that only small displacements are preferred, because when the displacement grows, there is a significant increase in a stress level. So again, we help them to understand what is the tripod behaviors and what is what parameters are influential to the total, to the overall result. We realized that the spring position does not affect the stress level. So it's good to work with those positions because it can affect the movement of the total, of the optical element, but it's not increasing the stress levels that much as those displacements. And again, we had 12 parameters, input parameters, and 10 results, and we were do it quickly. We only needed 155 FEM computations in order to build a very precise model. And because we realized that some of the input parameters are not important at all, we were able to simplify the whole design of the task. And the last one is called pressurized body. This is a lightweight body part. It's a mock-up of some turbine engine, and we made this task in cooperation with Brno University of Technology. And the goal was to find out what is the influence of stiffeners located on different diameters on this part. The ultimate goal was to improve the safety factor while keeping the weight of the structure. We had there 16 inputs, width and height of stiffeners, and they were split into 8 segments. So some of them were on the edges, some of them were in the middle. Again, it was done in FEM environment MSc Nastran. We started with sensitivity analysis and realized that stiffeners that are on the edges have really low impact on stability. So it means that we completely had to focus on those that were in the middle of this part. This tool showed us something that is logical, but it proved that our tool is right. And this is the information that you need to always increase both height and width of each stiffener, because if you have a stiffener that is high enough but not wide enough, it will cause you a loss of stability. So both dimensions of each stiffeners have to be treated. Here you can see that if you don't treat the interactions of the geometry, it can again cause a tail that increase the probability of failure, because here's the area of stability loss. So again, it just confirmed that when it comes to stiffener, you need to always take care of width and height in any case. And at the last graph, you can see that stiffener height is most crucial for the stability improvement. So it has to be above 3 millimeters, because if it's below, there's a growth in a stability loss probability. And on the right, it's growing. So it means that it's better to achieve or build a higher stiffener. But as you can see, there is some region overlap, and this is again due to interactions. So if width wasn't enough, then it would mean that there would be increase in a probability of loss of stability again. In this case, we were able, by improving the geometry of this part, to increase the safety factor by 235% on average. So you can see the original distribution and the improved statistical result. And as you can see, again, it's a range. So it means there is enough space for production tolerances and so on. New ranges eliminated the stability loss, which was a goal. And we were able to select only the important geometrical parameters for further design. So it means that by deleting some stiffeners that were on the edges, we were able not to maintain the weight of the part, but even to decrease the weight itself. So this was the third case. I would just add here that all of them were in FEM. This wasn't my intention. I realized it right now, but we can work with a CFD, thermodynamics, and or any other simulation as well, because as I said, our tool is purely mathematic. We only work with the numerical inputs and results. So it has, we have no problem to connect it to any other simulation platform. Here you can see some other case studies that we were working on. We were able to shorten up the landing ground distance of commuter airplane by 18%. By improving the flapped airfoil. We helped to increase the glide ratio, or yeah, this is another part of the case study that I was talking about with Skoda. When we were working on a more complex case. You can take a look on each of them on our websites. There is a resources section, case studies, and you can take a look at it. We just finished some other pilot projects now, so we will be adding more soon. So if you're interested in the topic, look at our website, UptimAI, and you will find much more information there. We were incubated under ESA Business Incubator Center of Prague. Now we are backed up by private equity fund Lighthouse Ventures, so we are stable. And then we have, we are partnering with many universities, which is helping us to further improve our product. We work with industrial leaders as well. We have a lot of partners that works with the simulations that they are either reselling it as a service or reselling some simulation platform. So we are partnering with many organizations as that. And I'm coming to the end. We are really open to connect and talk about the possible cooperations. We are looking at the moment for resellers around the globe. We are looking for potential partners. We can provide you a tool for testing and so on. The offer that I prepared for today is that if anyone would be interested in buying our solution, we can offer a free implementation if there is a prepayment for the first year of cooperation. So if you're interested, feel free to get in touch with me. You have my contact details here, and yeah, feel free to ask anything that comes to your mind. And thank you very much for your attention.